Thanks very much, Drew.
Thank you.
Thank you very much for that fine introduction. And thank you for the opportunity to speak with you all today and provide a government perspective to augment the academic work and the industrial work that we know is going on and we heard a bit about this morning. This is really going to be a team effort, you know, and I think one of the things that's been difficult over the years to grapple with has been the multidisciplinary aspects of the challenges here. So it's great to see this wonderful environment, trying to bring together all of those disciplines. Last night we had a tour and we saw the dancers and the producers intermingled with the high technology people, trying to grapple with crossing those disciplinary boundaries, breaking those down to find new sources of innovation. It was also gratifying as a person who spent, I guess, most of my whole career here in upstate New York. I went to Cornell for undergraduate and graduate school. And then after 4 years out teaching in Dayton at the Air Force's graduate school, I came to work at Rome Lab, which has gone through several name changes over the years, but was there for 27 years, rising up to be the chief scientist, as you mentioned a minute ago. And that's the information directorate. Now, but we need to bring more than just that batch of technologies to solve many of the problems. So it was gratifying to see this Project Jefferson, for example, where many disciplines are going to come together: biology, chemistry, weather, certainly the computational side, to help protect some of the great resources. You know, Lake George here. I have many fond family memories of boating and camping in the state parks at Lake George. Good to see that it'll be protected by the combined creativity of multidisciplinary talent. That kind of coming together can have great effect in that one instance, but that's exactly the sort of thing that we need to be able to do time and again to deliver new capability, to protect the resources we want to hand down to our children to enjoy in future generations. So today I would like to take a few minutes and talk to you about DoD interests in autonomy and AI and augmentation, which are manyfold. DoD's a big place, employs a lot of people, has a broad mission set, and so on the one hand we have people going in harm's way, sometimes in small teams. What kind of automation can they take to be more effective, safer, and doing what in many cases is an inherently dangerous job? But we also have large operational centers and situation rooms, which were very much akin to what we saw earlier today in the presentations by President Jackson and Dr. Kelly. So I'd like to give you a broad brush of the department's interests, but also talk from a technology point a bit. My personal background is in high-performance computing architectures, particularly ones for small little embedded spaces where there's not a lot of power to be had, and yet we want all of these smarts. Over time, I also got into neuromorphic computing architecture, so I know a bit. So on some of those slides, I might go a bit deeper. But in recent years, the last 5 or 6 years, I've been leading the department's efforts in cyber and science and technology improvements that could help change the game in cyberspace, which I think many of us have received letters in the mail from either your healthcare provider, your credit card company, for me, from the Office of Personnel Management, all saying, I've been had 6 ways to Sunday, and couldn't we somehow recreate this environment to be more secure going forward? So many different challenges at different levels. So as I'd like to just have some overview for you and then talk about autonomy and then AI in these kind of areas. But you know, first we have to put up your favorite caveat about predicting the future, because I'm going to get into it. And I want to say that these are not official Department of Defense projections, perhaps, in some of these cases, but my own thoughts from having been engaged in this for a while now. But you know, looking back over the long term, technology advances have had that transformative impact time and again, right? Whether it's the catapult, the longbow, the Tommy gun, the tank, But then you start to see a transition into more information-centric things. You know, in most of our modern fighters, there are millions of lines of software. And I think I've seen estimates of 80 to 90% of the functionality in those fighters is actually implemented in the software. So it's changing from the physical aspects of things to more the information, or perhaps now we want to move into the cognitive capabilities of these systems are really where they deliver definitive warfighting capability. So the value of autonomy to DoD is great. You know, it can enable many things. And in general, we're not looking for fully autonomous systems, certainly for the application of force. There's a policy that's actually been written on that, and humans are going to be in that loop. However, for things like persistent surveillance, where human fatigue, you know, we've got aerial vehicles that can stay up for 72 hours, for example, and people need sleep somewhere in those kind of time frames. So, you know, for watchful eyes that are always looking to understand and then report back, we're definitely interested in those areas. Matter of fact, you know, in trying to get this briefing approved to give to you today, it went through interesting leaps and bounds because, as we mentioned just moments ago, everybody is interested in this. If you haven't seen the Deputy Secretary of Defense's remarks a couple of weeks ago at the Reagan National Defense Forum, you should, because he's, you know, the #2 guy in the department and was taking a pretty affirmative stance in this area, that the ability to get this right, this human-machine teaming, was perhaps of many different technologies, the transformative technology that could lead to a new offset strategy. Now, an offset strategy is something that puts us a significant leap ahead of the adversaries. We've had a couple, you know, tactical nuclear weapons maybe were the first, and then in the Gulf War, you know, how there was that shock and awe of precision weapons dropping down with pinpoint, hit the cursor. We all saw that on TV, dramatic effect. The next leap ahead is posited to be, you know, getting this type of technology that we're here to discuss correct. So I'd say that there is great interest and perceived great value in doing this. There are also risks, and there are considerable technical challenges in doing this that I'd like to discuss. But here are some of the operational challenges that we can hopefully really see ways to impact. We've got limited manpower, and yet we want to do many things. How can we make each and every valued person that we bring onto our team that much more effective and efficient? Then we have some harsh environments. This nuclear accident that President Jackson talked about, you know, we don't want to be sending people into those types of harsh conditions. If we can send, you know, autonomous systems or teamed human autonomous systems in instead. DoD is faced with many situations like that. Clearing minefields isn't something that you'd like to put on your day job resume. You know, there's some things that we would easily look to autonomous systems to help avoid harsh and dangerous environments. A rapid response, 24/7 presence. I mentioned persistent surveillance. That's a good example of needs in that area. New mission capabilities, I'll talk a bit more specifically about, but there are many on the next slide. Advances in medical applications, boy, I think you really hit the nail on the head there. Obviously, industry fully understands that that's a major market segment, while DoD has its own needs to deliver health care, often in, you know, emergency room type situations. And then just capabilities beyond human limits. I mean, the ability to track all the traffic in a city, what my cell phone is now routinely doing for me, how I got here this morning, and optimally routing me in the face of the traffic, you know, between Albany and Troy, and always getting there is really beyond human comprehension, you know, to perceive that. And if we drop back to our old way of doing it with static maps, it's not nearly as adaptive to the conditions of the day as what we now enjoy. So here are some of those operational capabilities that we would need to have. The ability to move lots of data and to make decisions is fundamentally one of the things we have to do, but we have to also be able to have a forward presence, often with limited communications, because this is let's say this is a hostile environment. There's blue and there's red up here. And so while we are trying to communicate, sometimes those communications are going to be jammed or denied in other ways. So that actually puts quite a value on the system being smart enough to be able to carry on and conduct the mission in the presence of intermittent or complete communication outages, for example. Smart weapons that can understand and go after their targets are part of that. And autonomy finds itself embedded in many places, not just in the weapons and the aircraft, but throughout the system. We are trying to, standing back from the fight, develop intelligence products about what's going on, how is this whole thing proceeding, and what should we do about it? And that often involves this mountain of data that we have to comb through. So DoD has its own sets of big data challenges. And oftentimes, some of the R&D needs that we find are to be able to get some of these cognitive capabilities, but in small packages, where the size, the weight, the power are limited. And also, by the way, the cost can't be enormous. I mean, if you're going to make a $100 million aircraft or a $1 million missile, you can't afford to have so many of those kind of things. So, hate to be too greedy, but we're physically constrained in terms of the embodiment often, and the price tag also has to be constrained. Now, added onto this is one vexing thing that I really have dived into in recent years, which is this cyber-hardened word. So in addition to all of those nice attributes, maybe the attribute of cyber-hardened needs to move up in the chain of adjectives. So the chain of adjectives might be high performance, low cost, capable, but then also resilient to cyber attack, because this is an increasing reality in our world. This has some things, some attributes of how you might do that really need to be talked about openly in the community, and some attributes don't need to be talked about openly in the community. But to some extent, logical approaches to that would be to know what your system is, to be able to trust in your hardware and the software. I mean, if you've just got a black box that somebody gave you and it has a purported behavior, you know, you'll be concerned that maybe there's other software in that black box that has a completely different behavior that right at the wrong time will jump out and bite you. And this was completely deliberate and done beforehand. So it calls for an openness in the specification of the hardware and the software to lead to a trust from a cyber point of view. But better business interests can be diametrically opposed to this, because propriety and profit are tightly coupled words, right? If everybody knows exactly how you did it, then they can recreate the capability that you did, and you'll have competitors nipping at your ankles in just a moment. So I think that there is really some discussions to be had here. I think actually that there's a solution where propriety can be held at a higher level, maybe where there's an app for that. But in terms of the foundations, more openness may be required. Good debate to be had around this point. But it relates back to one of the fundamental problems that we have had and will have with the development of autonomous and cognitive systems, which is, can you trust these things? That is a foundational issue. Now, this isn't because they've been hacked from a cyber point of view. This is just because we've got so much evidence that software systems often go awry and don't behave exactly the way we'd like. And those weren't even software systems that were rewriting the software, as it were, or learning on the fly. So how do we gain trust and confidence in systems, period? But from a cyber point of view, we get even more paranoid about this. Now, these two things could play together nicely, because the cyber paranoia could motivate us to opening up the foundations of the systems and getting provable properties about the systems asserted. And that, in turn, could help provide a better foundation for building autonomous systems. But these are some of the S&T challenges that we have. So the one I was just talking about is test, evaluation, verification, validation. How do you do that? That's tough to do when you have a static set of software in a normal system and you're trying to run it through all its paces, when it is typically these days 2 to 30 million lines of code. That's a tough design space to fully characterize and validate, much less when it's a moving target because its behaviors have now somewhat become part of its growing up, if you will. Machine learning, reasoning, and intelligence are obviously core technical underpinnings to this. And there have been some interesting developments. I guess Dr. Kelly was mentioning going through the winter of AI or whatever. I completely agree. I think the US, in many regards, felt AI had overpromised and backed away quite consciously. But it's, we've definitely taken note of the fact that things can change over time. Breakthroughs recently in deep learning particularly, really showing much better performance on a number of key benchmarks, may be a great cause for a reassessment at that time, and we're definitely engaged in that. Let me talk about the computers and the human brains for a bit. Now, I love some of these metrics, being a computer architecture person. The numbers are debatable, though, in terms of the scale. So let's just set the left and the right a little bit here, and give me a couple orders of magnitude, perhaps, you know, for the sake of argument. But the Sequoia computer is one of the nation's largest, about a 20 petaflop machine. It dissipates more than 1 megawatt. It dissipates about 8 megawatts. Actually, since I'm here at RPI, happy to mention that at Rome, we did some nice groundbreaking collaboration with both IBM, the Livermore guys who host Sequoia out in California, and Professor Carruthers here, because this computer made by IBM has some special networks which really enable it to do discrete event simulations, which are really important. That's like cyber warfare simulations and communication network modeling and simulation. Really speeds those things up, where other supercomputers kind of roll over and die on that particular form of simulation. And it was interesting to run on Sequoia when it was actually a little bigger than it is presently, because they had the classified machine and the unclassified machine brought together for a brief instant in time, 2 million cores, as I recall. And to watch it simulate 500 million events per second was orders of magnitude advance over where we had been before, in part because of the sheer magnitude of the machine, in part because it had special characteristics. So it's a good one to compare. It's still number 3 on the top 500 list. I was just checking that last night because you know, the supercomputing meeting, the SC meeting, is going on now. And but how far away is it from where the human brain is? Now, the brain, the watts are really different. We've got a big gap to close with watts. But, you know, 100,000-fold seems quite daunting. But I would point out here, you know, we're working with IBM on this True North chip, and that touts a 10,000-fold improvement in power efficiency. Well, that would close a lot of that gap pretty quickly. So there are definitely things that can be done in architecture land to get at some of these larger gaps, but certainly power dissipation is one of those differences. Now, on the mini-column level, we've done a good bit of research at Rome in large-scale neuromorphic modeling and simulation, and in particular focusing on the mini-column level. You know, I remember writing a proposal that when we built a supercomputer out of 2,000 PlayStation 3s, thanks to Sony and IBM on that one too, we really wanted an affordable way to get at that cell broadband engine chip that was inside the PlayStation 3. We worked hard on optimizing some brain state-in-a-box neuromorphic models from Jim Anderson down at Brown, and got very high percentage of peak on that. So I think actually back in those days, a half a petaflop might actually do half of a brain at a mini-column level. Certainly we've gone well beyond that with 20 petaflop machines, and now the president announces an accelerated effort to get us to an exascale machine. On an exascale machine, which would be 2 to the 18th you could get many operations against those numbers of synapses and neurons. So I think we're in very interesting times where these sizes of computers actually could be expected to do a considerable job of real-time simulation at these various levels of abstraction, but can we get the goods out of the computer cycles? We've been making some significant investments in the area of autonomy. This research pilot initiative, chief among them, $15 million a year investment through this fiscal year that's going on now in a number of cross-cutting areas. And this has kind of been building up the community across the services, because most all of these proposals or activities, these projects are multi-service engagements. So we've been nurturing a community working in this area of autonomy with a variety of projects that you can see here that span different places where autonomy would reasonably fit into the department's objectives. Now, as a complement to that, the Navy's also got work in the foundational science base of autonomy, and you can see that they're addressing some of these same S&T challenges. How do we get the human unmanned system collaboration done correctly? How do we scale this thing up? A challenge that you heard earlier today. And how do we get the perception and the intelligence to drive the decision-making that we want? Some of the multidisciplinary challenges, again, relate to experimentation both in the field and in a simulated world, as well as trying to provide a better mathematical underpinning to this. And that really gets to that underlying issue of trust that I think will be fundamental to advances of this technology base really getting out into the field. Let me talk briefly about something more specific that you might be interested in. So we're working on very cyber-hardened processors with excellent power efficiency that would be these secure processors, in this case shown to go in a pod that could go under the wing of an aircraft or a UAV. But somehow, like the neocortex wrapped around the old cortex, we've got a problem of old aircraft that still fly well, but we want to put a lot of new smarts into these aircraft to go against modern technologies for this dynamic fight of electronic warfare versus our communications and things like that. How do we do that without busting the budget? Maybe you can give me a pod that rides under the wing that has the new tech in it. And what might that be? Well, something borrowed, something blue. I guess that works really well with IBM, but in this case, we need some of that conventional high-performance computing, but it's got to be very power efficient. And the target figure of merit there is we think in 14-nanometer trusted foundry line, we can hit 100 gigaflops per watt. So you can get several teraflops for 10 watts. And we think that's a good balance point for doing a lot of real-time signal processing. But then the decision engine, that mesh connects into, in this case, we're working with the true north processors and driving the conventional computing into the more neuromorphic computing on the right. Because that's where you've got that tremendous power efficiency of 1 million neurons, 70 milliwatts, those kind of numbers, which are very impressive. So we are actively exploring this at the Air Force Research Lab now. Some work that we're interested in, text extraction. I think we talked a lot about this before. The military runs into some interesting real-time text extraction problems. For example, when a team would maybe break into a safe house and people scatter or are taken down, and then you have books and you have computers and you have all these things. You very rapidly, before the command and control network changes, you want to be able to find the interesting information in all of that reference material. And humans can't read it fast enough. So we did some work on occluded text recognition, occluding meaning you can black out some of the characters. And actually on that supercomputer with 2,000 PlayStations, the PlayStations were running that brain state in a box model, and the Xeons were running another model, a confabulation model that Robert Heck Nielsen put forward. And those two models work very well together to fill in the blanks. So the confabulation would have been trained up on reading a whole bunch of books and could anticipate what the word before and the word after would be, and even sentence fragments, getting very high performance. And in the end, this one's reading 21 pages a second. And then that feeds up into the text extraction algorithms, some of which you heard about before. So this would be a helpful compatriot to bring along to do the rapid, real-time exploitation of information, and then feeding back to the humans the good stuff. Now that's a challenge for these text extraction algorithms, to discern the relative importance of a whole volume of information. We have a variety of multi-university research initiatives going on. These are funded by the Office of Naval Research, some on knowledge representation and learning. So a big focus on computer vision here, you can see, because we, like most everybody else, have a multiplicity of feeds coming at us from the camera sensors that are all over. But then also the one on the bottom focuses more on what may be a key trick, which is, I think, an innately human ability, well, it's not only human, to find reduced dimensionality spaces within which to reason. Because we're easily overwhelmed by the exponential blow-up of state spaces if we can't find these simplifying, I equate this to kind of an eigenvector analysis, or more appropriately, a singular value type analysis, where you can actually do rank estimation and then tune your system to the observed rank of the complexity of the processes that you're looking at. Also, Muri's on embedding humans in the loop with these automations, and some work on representations, and also focusing on the visual domain. So lots of focus on the visual domain at the current time. Hold that thought, come back to that in a minute. Now, thinking about AI, it was brought up before, we've been at this. We've seen this vision for 50 years or more. And the DoD was there in the very earliest days, understanding that, my gosh, if we could do this, it would have tremendous impacts on our mission space. And so all of these, lots of DARPA investments over the years, you can see here a little play in the work that led to Siri down at the bottom. But And things not even on the slide, like the Architectures for Cognitive Information Processing program, which I believe led to the True North chip, vis-a-vis the IBM submission to that program. So we've been about it, but yes, I've got to say that we backed off. We actually lost funding and people in this area across the service laboratories at different points in time. So people might be a bit skittish to jump back in. Nevertheless, recent advances seem to motivate us to do exactly that. And these are some of those recent advances which are delivering impressive results and a second look. So I'm on a committee of folks across government to have another look at AI. Actually, the first time that people from the Office of Science and Technology Policy asked me to be on a committee about AI, I said, did you say AI? Did you mean to say AI? We kind of dropped that, 2 decades ago, but they seriously meant to say it. So there's an honest reconsideration. One of the reasons I'm very happy to be here today, because we see industry moving out perhaps more rapidly than the government, but all of these innate opportunities for us to benefit have been and still are there. On the Army Research Labs part, there are some collaborative technology investments. As you would expect, the Army should be actively engaged in robotics, and they are. With a number of members here under this technology alliance, this is a mixture of universities and industry, as you can see. Similarly, really trying to shrink these things down. If we can get down to bug-sized, I thought this octoroach was interesting, was Googling that up last night, fits in the palm of your hand. If we could even get down to bug size with the intelligence of bugs, actually, some bugs have a pretty impressive intelligence and an ability to survive and evade my fly swatter. I could imagine many places where we might like to be a bug on the wall, literally, if we could get the perception of what was valuable from being in that position. In neuromorphic computing, I think what you've seen here is that we're working hard on text and audio processing and imagery and video. Next most challenging, the bandwidths go up. But as came up briefly before, I think cyber presents even a more daunting application domain because of its inherent desire for low latency. And I know as a parallel processing person that if you tell me you need massive throughput, but you don't constrain me on latency, I can take an embarrassingly parallel approach. But if you tie my hands with low latency to win the fight, Then I've got to parallelize single tasks across multiple cores, and it's inherently harder. I think Mother Nature has already determined for us that latency is really a key parameter in survival. And in cyber warfare, low latency between sensing, perceiving what's going on, reasoning over it, and then taking action, the tightness of that loop is going to be critical for success in the domain. And so I think that probably is the most stressing of these cases. So what next? You know, the future of AI is very promising. It's been very heartening to see top leadership in the department recognize that of all the places, you know, they could have said hypersonic technology. They could have said nanotechnology. Of all those places, they really have zoomed right in on this area, and hence why this briefing went up and down the chain of command with everybody weighing in, pulling out my favorite slide, which I didn't get to tell you, but maybe I'll go into it a little bit, because it's too argumentative. But there's plenty to argue about in this area, but there's plenty to be gained from being successful in this area. If there's anything we've learned, though, we run into the Tower of Babel problem in this area. I remember the kickoff of that Architectures for Cognitive Information Processing, and we had probably the same collection of folks we have here, folks in neurobiology, folks in computer science and electrical engineering and physics and chemistry, all with a different language and difficult to come together. It's just a fact that nobody goes to school for long enough to master all of those. And so we do need to work together on this. We need to work together on this also in another dimension, across academia, government, industry. We understand that some of the principles that you might advocate to be successful and build trust in this area might demand openness, which would not be the first thing that business interests would gravitate to, okay? If McKinsey comes into your business and tells you that probably the right business answer is not to be open, right? But to keep your company's secret sauce and make boodles of money on it. However, in this area, we may need to have that open foundation because the fundamental problem that people have with it, and you even heard it echoed in the earlier questions, is should we trust this? What are the technical underpinnings that would ever get us to a position that we think we could trust these things to not run open loop and out of control, and to all the movies that we've already seen? So thank you for the invitation to come and talk with you today.